In this video, we will continue with moment diagrams. So the last video, we focused on moment diagrams when our beam only had point loads. In this video, we are going to learn how to draw moment diagrams when your beams have distributed loads. So here's your distributed load. Pretty simple. You have your distributed load throughout the entire beam span and your supports on either end. So let's talk a little bit about the shear diagrams again. So point loads happened at an instant. Because it happened at an instant, there was no slope for the shear diagram. And there was a linear slope for the moment diagram. Distributed loads are constantly applying more shear force per unit of time. And because for every 1 foot you went along the beam, you were experiencing more shear force, we said that there was a linear slope for the shear diagram. So the moment diagram would actually have a quadratic curve. And for those in calculus, I think that should make sense to you. So this slide right here is more for those in calculus. If you have a shear point force, P, and then you did the integral of a point load, P would be a horizontal line. If you took the integral of a horizontal line, you would get a linear line. If you took the integral of a linear line, you would have a quadratic curve. That's what's going on here. This is a real-world example of calculus with derivatives and integrals and things like that. We are interested in the area underneath a curve. For those not in calculus, let's just have a quick chart to summarize. If you have a point load, on the beam load, it just is an arrow at that individual point. Then, on the shear diagram, those point loads then create horizontal lines and rectangular shapes. Then the moment diagram, when you do the area underneath a rectangle, the geometric shape would be a linear line, or like a triangle, like y equals mx plus b. Distributed loads would look like a rectangle for the beam loading, because you have the, let's go back, here's your rectangular shape for your beam loading. And then the area under that, when drawn out as a geometric form, would be a triangular shape. And the area underneath that, as a geometric form, would be quadratic. So it would be kind of a curved shape. If you can kind of follow my mouse, it'd be a nice curved shape. What's that? Concave, I believe? I don't remember it's been a while. Okay, let's go right to an example. Create the moment diagram and determine the maximum bending moment the beam will face. We have your 100 pounds per foot distributed load. And step 1, as will be common, you need to find the reactionary forces. So it's going to be half to each side, so 100 times half the distance, 1,000 to each side. Next, you would need to draw the shear diagram. And you should know that you go up 1,000, and then for every 1 foot you move over, you go down 100. Your slope is negative 100. So there would be your shear diagram. So I see 2 triangles. Each triangle has a height of 1,000 and a length of 10. In this example, they happen to be the same. This is symmetrically loaded, so this triangle right here is going to be the same as this triangle right here. So we're going to calculate the area of that shape. You should know that the area of a triangle is 1/2 base times height. So 1/2 times 10 times 1,000 gives me 5,000 kip feet. So the maximum moment is 5,000 kip feet. And here is what that would look like. Like we said in the previous slide, if you have a distributed load, it's a triangle in shear and then a curved shape in the moment. So we start at 0, we curve up to the height of 5,000 kip feet, which is the area of this right here. One quick mistake that I just realized is I have pounds here, so this should actually be pound feet. I'll change that out for what I upload, but just to keep the consistency. I just found a mistake and I'm not editing the video because I don't care enough. So that should be pound, because you're multiplying pounds by feet. It should be pound feet right here. In fact, I'll make you watch me to change it. And I can't change that. Crap. Oh well. You get the idea. Okay. So, your turn. We have a simple beam with the load of 1,090 pounds per feet and a span of 18 feet. And I want you to draw it out. Pause the video after I'm done with the sentence, and I want you to draw the shear in the moment diagram. And if you're not going to draw it out, which I'm sure 90% of you won't, at least pause the video and think through what you would do. Like, give me the process. Calculate the numbers. Make sure you understand. Don't just nod your head when I say it. So pause the video now and proceed. Okay. I'm going with the presumption that you did talk through it, and here are the results. Here's your shear, triangular shape, and then your moment, which is curved in shape. And then your maximum right here, 44,145, is the area of this triangle right here. We go up, and then this area right here is negative, so we actually go back down to 0. Okay, lesson 3 is we are going to draw the moment diagram when you have both distributed and point loads. And these are more challenging. Let me give you that warning right now. So here's your beam. You have a distributed load throughout the entire span, and you have a point load 6 feet from the edge, which is not in the middle. It's not symmetrical. So in here, notice that the reactionary forces are given. F of A is 9,300. F of B is 7,700. Again, I won't always be giving you that. So your first step would be to draw the shear diagram. You should always draw the shear diagram first. You should never go straight to moment diagrams. So what would that look like? Well, here's your shear. You're going up 9,300. You're going down 650 pounds per foot, and I'm doing that for 6 feet. So right here, I'm dropping down 3,900. Then at that moment, I drop 4,000 real quick, bringing me to 1,400. And then I continue losing 650 pounds per foot for 14 more feet, which gives me negative 7,700. And at that point, F of B brings me back to 0. So now I'm going to have to figure out the moment. And the moment is still going to be the area of the geometric shapes. So what geometric shapes do you see here? I see a trapezoid right here, a little tiny triangle, and then a bigger triangle. And since we have distributed load going through the entire span, all the moment diagram will be a curved shape. So let's now figure out the areas. So the area of this trapezoid right there is going to be, well, I just want to say, from my experience, I feel like high schoolers hate finding the area of a trapezoid. I don't know why. But a lot of you would rather break this into a triangle and then a rectangle. If that's you, fine. Find the area of the rectangle and the triangle and add them together. Totally fine. But the area of a trapezoid is 1/2 the height 1 plus the height 2 multiplied by this base, which is essentially you taking the average of those two heights and then multiplying it by the base to make it a rectangle. So we have 1/2 times the sum of 9,300 and 5,400 multiplied by 6, which gives you 44,100. Oh, I did it again. This should be pounds, not kips. Now we will find the area of the triangle, which is going to be a little more difficult because we don't know the length of x right here. And x is where it's crossing the x-axis. So before we can actually find the area of the triangle, we got to figure out where it's crossing the x-axis. And this is why this is more difficult of a problem. We have to pause and figure this out first. So we're going to figure out x by using the slope-intercept formula, which is y equals mx plus b. And in this case, y is the shear force at that point. And you should realize that the shear force at that point is 0. X is the horizontal distance, and then B is your starting shear force, which is 1400. So we have 0 equals negative 650x. 650 is your slope because that's the distributed load. It was 650 pounds per foot. Plus the starting, which is 1400. And we're solving for x, which is x equals 2.15. And let me just say, here is a shortcut to find x. And you will be able to do this shortcut every single problem. All you have to do is take your starting shear for that line and then divide by the slope. So take 1400 and divide by 650. X equals 2.15. Just do that every single time. Don't do this, do this. Take your starting, divide by your slope, boom, done. Now I'm able to go back to this slide, and now I can get the area of the triangle. 1/2 base times height equals 1,505 kip feet. Okay, cool. So remember, all shapes above the beam are positive and are added. Everything below is subtracted. And the maximum should then appear at the point along the beam where the shear diagram is equal to 0. This is an important bullet right here. The maximum moment will occur where the shear is 0. And again, some of you in calculus might have made the connection of, oh, max and min, that's kind of the point of inflection type of thing. Also, the total area above the beam must be equal to the area below the beam. The moment diagram must start and end at 0, and let's see what we can draw out. So, here is your finished moment diagram. So, our positive moments are going to be from this trapezoid right here. We calculated the area to be 44,100. Again, I wrote kips, this should be pounds. No, I'm not changing it. So right here is 44,100 pound-foot. Then we have a little kink from one curve to the next curve. But this little area right here, the area of the triangle, is 1,505 pound-feet. And we're going to be adding to this. So we're starting at 44,100 and then we're adding 1,505. And that's going to give me my maximum moment. Now I have negative moment caused by this area right here, this triangle. So the area of that triangle is 1/2 base times height. And this length right here does take a little bit of calculating. I know my total length is 20. So 20 minus 6 minus 2.15 will give me that length. That'll be my base, and then my height is negative 7,700. And that gives me an area of 45,622 pound-feet. And the max moment would be the sum of all positive moments or the sum of all negative moments. And just as a note, I don't know if you can see that, my little bar is right there. These two should be exactly the same. The reason why they're slightly different is just because of rounding. So here's just showing you an alternate way of looking at it, in that you can add it up by just doing triangle, rectangle, triangle, if that's easier. And here is your finished moment diagram. Let's just talk through it first. You find the shear, then you get the area underneath the shear diagram. This area is this value right here. Notice how it lines up. Because this is above the x-axis, you're going to add this area of the triangle, which gives you another 1,505, is that what it was? And that's your maximum moment because we're at where the shear is 0. And then we go down this value right here. And even though the values of the areas weren't exactly the same because of rounding, we know that it's going back to where it started from. So then we just curve back down to 0. And that concludes moment diagrams.